Today we're going to be looking at designing a video streaming platform, something similar to YouTube. Now, we all know what YouTube is. It's one of the most popular video streaming services where users upload, stream, search, and comment on videos. It's a free video hosting platform, and it's one of the most viewed websites in the world after Google. So let's design it. So as always, let's start by defining the requirements of the system so that we can understand the scope of what we're building here. So firstly, we have the functional and non-functional requirements. Now, there's quite a lot here. So let's go through them. So content creators should be able to upload videos. Users should also be able to search for a video and see the view count of that video. Users should be able to stream videos on all devices. Thumbnails need to be generated for each video, 3 minimum. Now, in terms of non-functional requirements, we have high availability and reliability. So consistency in this system can take a hit. We need to ensure low latency. So when users watch videos, there should be minimal buffering. This is going to be for a global system, and the system must optimize storage capacity. Because it's global, we are going to be storing a huge amount of data. So we need to look at optimizing this. Now that requirements are out the way, let's dive into the capacity planning and estimations. Initially, there is a lot to take on board, but we're going to go through this step by step. Let's have a look at the assumptions first. We have to make a fair few assumptions within this system. So let's assume there's 4 billion users in total. 1 billion of these are daily active users, so it's a huge system. There are 500 million videos, which is a modest amount. 1 million daily uploads. Average videos viewed per user is equal to 2, and this is per day. Average video length is 5 minutes. So 20 minutes of HD equates to around 1 gigabyte, which equates to 1 minute being 50 megabytes. And then after transcoding, say this is roughly 100 megabytes. So based on that information, the average video size is going to be 500 megabytes, 100 megabytes times 5, because we're looking at 5 minutes here. So let's start off with calculating traffic. We have 1 billion daily active users, each of which are going to be watching 2 videos. So that's 2 billion views per day. Now, per day isn't that useful to us. So we need to convert it into something more useful. So let's convert it to per second. So we have reads per second, writes per second. We know that there are 86,400 seconds within a day, so let's round that up to 100k. Let's divide the 2 billion we've just calculated of views per day by 100k to get views per second. So we have 20k reads per second, which again is rather large. Read to write ratio is 200 to 1. This system is going to be read heavy, right? Because more people are going to be watching than they're going to be uploading. So if we divide 20k by 200, we get 100 writes per second. And based on this information, we can now work out storage. So we have 500 million videos, each of which are roughly 500 megabytes in data. So this is 250 petabytes as a base. Now, if we grab the 2 billion views per day and we divide it by 200, so the read in the read to writes ratio, we will get the amount of writes that are carried out per day. So that's 10 million writes per day. So if we times that by 500, that's 5 petabytes per day of extra storage needed for this system. Now, if you're struggling to work this out, just use the byte conversion table, which converts the unit of data to byte conversions. Next, we have 5 petabytes times 400. We know that there are 365 days within a year, but we don't want to times by 365. So let's round this up to 400 because we are estimating here. And this gives us 2 exabytes of data per year. Now, if we want free replicas for this and store this for 10 years, that's 80 exabytes of data. So this is a huge system. In terms of input output, we have 100 writes per second times the size of the data, which is 500 megabytes. That's 50 gigabytes per second. And then in terms of reads, we have 20,000 reads per second. Each is around 500 megabytes. So this is 10 petabytes per second. Again, this is in regards to a globally distributed system, and it's going to be over multiple server instances that will consume all of this bandwidth. So scaling is definitely something we're going to have to consider within this design. Now, when calculating the number of servers, if we assume that a single server handles 500 requests per second, then the number of servers we'll need for this, 20k divided by 500, which is 40 servers. Now, this isn't taking into account spikes within traffic, so we'll have to add configuration within the servers to auto scale here to accommodate for that spike in traffic during peak times. And also, 500 requests per second may be slightly high here, but this is just an example of how you could calculate the number of servers. Now, that was a lot to take in, so pause the video and read over this information, but enough with capacity planning. Let's move on to the high-level overview. So for the system, we have 3 main processes that are crucial for the design, and these are content creators need to be able to upload videos to the servers, as well as users being able to search and stream videos. So within the API, we have a service for each one of these, and this needs to be persisted within some kind of persistent storage. Now, this system is going to be rather complex, so let's split these up and begin looking at the API design and database schema for the upload process. So in the upload process, we have a post request at the endpoint /API/uploads. We're also going to pass in the parameters of video, title, description, and user ID. And once this is completed successfully, we're going to return a 201, successfully created. Now, in terms of the schema, this is going to be in regards to the metadata, of which we're probably going to use some type of relational DB. We have a users table, video table, and thumbnails table. Now, user contains all the basic information for a user. We have the primary key set to user ID, username, email, password, created at, and last logged in. With the video, this is the one we're going to mainly be concerned with, right? We have the video ID as the primary key. We have a foreign ID, which relates back to the user table. And then we have various information about the video itself with an object ref here, which indicates the type of storage we're going to be using to store videos. And we'll discuss how we can leverage views, status, and reference count later on in this design. And lastly, we have thumbnails. Thumbnails has the primary key of thumbnail ID. We have the foreign key, which relates back to the video that the thumbnail is concerned with. And we have the path. Similar to video's object ref, this is going to be directed to another storage containing the actual thumbnail. Now, these tables in the real world would contain much more information. For example, videos is going to contain other metadata about the video resolution, format, etc. But we've kept it to the bare minimum for simplicity here. So now we have a clear understanding of the API endpoint and the schema concerning the upload. Let's start formulating the actual flow of data and integrate all the components within this part of the system. If you like this content and want to know more about system design and data structure and algorithms, then head over to algojs.dev, where we've developed a platform with the sole purpose of streamlining your learning, covering a number of system design concepts such as design requirements, capacity planning, networking. We've even gone ahead and broken down some of the most popular designs. So think of chat applications like Slack, music streaming services like Spotify, and more. So that's algojs.dev. Go check it out. Now back to the video. There's a lot to unpack in this section, but it's super interesting. So let's get to it. So firstly, content creators are going to initiate an upload request, and it's going to be directed to the API servers, which comprise of web servers and application servers. So the web servers are for user requests and application servers are for processing the business logic. At this point, several pivotal tasks come into play. We have to update the metadata database. We have to transcode the videos coming in. So we have to convert them into different qualities and also use compression. We have to store the videos within the binary large object. We also have to generate the thumbnails and also store them within persistent storage. However, orchestrating these processes in this tightly coupled manner poses a significant challenge, given the anticipated upload rate of 100 videos per second, with each video averaging, say, 100 megabytes in its original size, so before transcoding. The cumulative load before transcoding would be 10 gigabytes per second. Now, recognizing this system's limitations, we need to look at an approach that initially stores the videos in a blob store before transcoding, followed by the subsequent retrieval by a set of dedicated transcoding servers to avoid this initial bottleneck and make the workflow more scalable. So let's look at how to build this out. So the post request comes in from the client. It goes through the web server. It reaches the application server. The server can respond with some kind of token indicating that the user has permission and can immediately store the video within a pre-transcoded blob, essentially a data dump. At the same time, the application server can generate an event message to a transcoding queue for that specific video that was just uploaded to the pre-transcoded blob. Now, some transcoding servers are going to be subscribed to this queue. They're going to be listening in for any events that come onto this queue. They're going to consume those, and then they're going to pull from the blob and start processing, start transcoding the videos, providing multiple qualities and also compression. Now, in terms of compression within the transcoding process, this is very domain specific, but I feel it's definitely useful to be aware of. So for our system, we're going to use a widely adopted codec for compression, and that is H.264. And this codec strikes a balance between video quality and compression efficiency. It's widely used for online streaming and has a broad support across devices, making it a popular choice in the industry. Now, while this is being processed, we can update the metadata database with relevant information about the video. And just like that, we decouple the processes. So let's think about the next step. What happens once these transcoders have finished processing the video? Well, the two main processes are storing the new transcoded video within different resolutions, so the bit rates, etc., and also update the metadata database with the video's new storage location, using the timestamp and also updating, say, the status enum to say F, indicating that it's been finished, so the video is ready to be viewed by the masses. So how are we going to achieve this? Well, the transcoding server, as you can already see, can push the new data within a different blob store called post-transcoded blob. Right, so here's where we're going to store the transcoded video files. Then, to keep the system decoupled, we can send a message to another queue. Let's call it transcoded meta queue. Workers are going to be listening into this queue, so they're going to be subscribed. They're going to pull from this queue, or the queue is essentially going to push directly to the workers information about those videos we've just uploaded to the blob store, and it's going to update the metadata with that information regarding those videos. It's going to update, say, the object ref and various other fields within that video table. Now there's one thing we still need to address, and that is the thumbnail generation. So there are a few approaches we could take. We could generate the thumbnails during the transcoding process. So the benefits of this approach is that the thumbnails are available immediately after transcoding, right? But the problem is it may add to the transcoding time within these servers. So instead, we could generate the thumbnails after within these workers, say, because we have access to the storage location of the videos, which is passed through the queue as part of the message. This keeps the system relatively simple, but now it's tightly coupled here with updating the metadata database. And if one of these components has an issue, this tight coupling will make it difficult to debug. So instead, what we've gone and done is have transcoding servers publish to another queue, which is called gen thumbnail queue, and these events are consumed by thumbnail gen handlers, which are essentially just a group of servers that sole purpose is to handle the thumbnail generation. And we have two options. We could either store it into a blob similar to the post-transcoded blob, but the problem with this is that from our capacity planning, we've worked out that there are 200 writes per second. We have 3 thumbnails needed to be generated for each of these. That's 600 thumbnails that need to be created per second. And if you think about it, when we're watching videos on YouTube, there's also 10 thumbnails on the right-hand side of the video. So this is going to require an extremely high read and write pattern. So while blob stores may be a valid solution, it's not the best solution for this scenario. So we know the thumbnails are small in size and there is a high read and write pattern with reads being excessively high. So what we can use here instead of the blob store is a wide column NoSQL database, such as Google Cloud Bigtable, which is specifically optimized to handle high frequency of read and write operations, making it a suitable candidate for storing these thumbnails. Now this part of the system is fully working. We just need to ensure that we're removing the raw video files from this pre-transcoded blob store to ensure that we aren't storing 2 copies of the same video in different storage locations, right? We need to optimize that storage capacity because we are storing around 80 exabytes of data. So a simple approach to solving this is to apply, say, TTL, so a time to live, for the pre-transcoded videos, so that they're automatically deleted after a certain time frame, reducing storage costs and maintaining a more efficient storage system. Now, before moving on, it would be a good idea to address some concerns with this current design. The first is we're trying to upload the entire video to the pre-transcoded blob store in one go. What happens if this process fails? If we had a retry mechanism in place, this would still mean that the entire video file has to be re-uploaded again. So that's not efficient. And the second is, what do we do in the case of duplicate videos stored within the blob store, right? We have 500 million videos in total with 10 million writes per day. There is going to be a non-trivial amount of duplicates stored in here, and we need to address this to optimize storage and reduce costs. So first, let's address this issue of the entire video being uploaded. Also, don't forget to subscribe to the channel. We are going to be publishing a lot more system design content over the coming months, so make sure you're always getting notified of new releases. So this is where we can employ resumable uploads, where the video file itself is essentially split into chunks and uploaded one by one, each containing a unique upload identifier and sequence number and timestamp. So how it works in the most simplest sense is we'll represent these chunks by like a chunk number, and start and finish. So the client initiates an upload process, goes to the application server, which is going to be processing all the business logic. The server responds with, say, a unique identifier and gives the user permission to upload directly to the pre-transcoded blob store. The video file is then divided into chunks. So say it's divided into this many chunks, and then the client uploads each chunk independently to the blob store. Now the application server will keep tabs on the pre-transcoded blob, so the server knows exactly which chunks this pre-transcoded blob has received. So let's say the client manages to upload to chunk 1, and then there is a network failure. When the client decides to resume the uploads, it sends a request with the unique identifier and information about the last successful upload chunk. It goes to the application server. The server identifies that the pre-transcoded blob has received chunk 1, and then it asks the client to resume from chunk 2, or chunk N here. So the client resumes from here, processes it, and then the final chunk. This way, even if the upload was paused or interrupted, the client and server can coordinate based on the unique identifier and the last successfully received chunk information, ensuring a smooth and efficient upload process. Next, in order to remove copied data, we can opt for a data deduplication process. Now, I'm not going to go into full depth into this because it does get quite complicated, but at a high level, we have 2 options to choose from. We have real-time, so pre-processing or in-processing, which is synchronous, or we have post-processing, which is async. So the real-time deduplication occurs before the videos have been stored within the post-transcoded blob, or we could do it afterwards. And what we're going to do is opt for the async process so that the transcoding can occur seamlessly without any interruptions. Now, one potential way for this to work is to have a scheduler or cron job in place that runs at specific points in the day. So in the background, we have these deduplication servers. And when this cron job runs, it's going to trigger these to begin searching within the post-transcoded blob and analyze the content of each video to identify duplicate patterns. It may use algorithms to compare chunks and determine if they're identical or similar. And then after the deduplication process, the metadata is updated to reflect that deduplicated state. So for example, the file location or reference of the stored video file may be updated after duplication, so it knows now to point to the unique deduplicated version of the video in the blob store. Now you may be thinking, what happens if the original video is deleted? Then all copies referencing that video would also be deleted. Well, here is where the reference count to our video table comes in. Remember this value right here. When a new video is added to the system, the reference count is initialized to 1. Whenever a new reference to a video is created, so there's a copy, it increments this count. If the count is greater than 1 when we're removing a duplicate, we just decrement this. But if the count becomes 1 and you plan on deleting a video, then this will go to 0 and we will process the deletion of this video. Okay, so that's a lot to take in so far. So go back over the video, make sure you understand the upload section. Then next, we're going to take a look at the streaming section. So for this design and requirements, we can streamline the query patterns to only include searching videos by popularity, so say view count, also searching videos by word, and also get thumbnails. So most viewed doesn't contain any parameters, it's just going to return the most viewed videos, and it's going to return information about that. So video, title, views, etc. In terms of search, well, if you search, you're going to have to pass in a query, which is going to be set to a string, and then we're going to get a list of matching videos, which would be paginated of some kind. And then finally, with the thumbnails, we are going to have to pass in a video ID to get the thumbnail for that video, and then this will pass back the URL or the binary data for that thumbnail. The schema is very much the same. We haven't added any extras to this. However, I should note, for the thumbnail, we could leverage the use of secondary indexes to improve the lookup operations by adding an index on the foreign key of video ID. Now, for generating a search result to users based on most views, we can employ a similar approach to that which we used when designing Spotify's popularity count. So rather than overloading the metadata database with constant writes to the views field, so every time a user views a video, it's going to have to directly update the metadata. So instead of doing this and potentially overload the system with writes, we can use a distributed hash table or KV store that's going to store a mapping of video ID and count. Then at regular intervals, we'll have a cron job that triggers these popularity servers to pull the counts from this KV store and then insert them into a queue, which is then consumed by these workers, which are going to batch update the metadata, so significantly reducing the load on this persistent storage. And you might be able to tell from this configuration that we are going to be opting for eventual consistency here, because the seamless user experience within the system is more important than the consistency of the view count. So by adopting this queue-based approach and modularizing this aspect of the system into distinct components, we've achieved a clear separation of concerns. The KV store and the queue components are dedicated to managing the immediate and intermediate phases of view counting, each with its specific role, where they operate independently of the primary metadata database. In contrast to the initial approach, where the view count logic was part of the retrieval process of videos, any issues within the view count logic would have been much more difficult to debug. So now the users can view videos based on view count. Next, we have to work out a way to search by keyword. And this section could be a lesson in itself. But in order for us to build an efficient full text search system, we're going to be using an inverted index data structure that maps words or terms to their occurrences in a set of documents. So something like Elasticsearch, which is built on top of an inverted index. And the best way to explain this is by using an example. So say we have two videos based on data structures and algorithms and system design. One which says exploring data structures in JavaScript. The second says system design patterns in JavaScript. So this has the ID of 1, this has the ID of 2. Now the inverted index is simply going to look like this. So exploring is only found within 1. It's going to be mapped to the video with the ID of 1. Data structures is also found in 1. JavaScript now is found in both. So this is going to be mapped to 1 and 2, so both videos. System design mapped to 2, patterns mapped to 2. So this could be integrated into the upload process. So as the upload process is being carried out, we could have another background process that generates an inverted index for relevant keywords in the video title. Then when the query comes in, our system can identify keywords within the query, look up in the inverted index the video ID, and very quickly generate a paginated response to the user. This will allow us to efficiently look up videos based on keywords, not only significantly reducing search times, but also introducing a level of flexibility and scalability to the overall architecture. Now with our current configuration, users are going to have to download the entire file before watching, which is definitely going to impact user experience and reduce the amount of returning users. And this is where streaming protocols come in. So streaming protocols address the challenges of delivering video content over the internet by allowing for real-time transmission, enabling users to watch videos without waiting for the entire file to download. And this solves the issue related to buffering, allows for faster start times and a smoother viewing experience. So we're going to look at two of the most common ones. We have MPEG-, which is dynamic adaptive streaming over HTTP, and we also have HLS, which is HTTP live streaming. Now, both these protocols provide us with the ability to divide videos into smaller segments or chunks, each encoded at different bit rates, as you can see here. Now, the cool thing about these streaming protocols is that the client can dynamically switch between the bit rates based on the client's internet speed. So it can continuously monitor the network conditions and adapt by fetching segments at a suitable bitrate, providing a smoother viewing experience, reducing the need for buffering. So you may even have noticed this yourself when you first open a YouTube video. The quality is sometimes poor within the first few frames. Then as soon as the first few frames are passed, it's a perfect, crisp image. This is what's happening in the background. It's an extremely cool process and very interesting. Now with these two protocols, MPEG- is the standardized solution to streaming with wide support, whereas HLS is particularly associated with Apple devices and browsers. So it's the default streaming protocol in iOS devices and macOS devices. Now, based on these key points and one of our functional requirements being that videos need to be streamed on all devices, we could opt for a hybrid approach here, offering us the best of both worlds and ensuring a seamless streaming experience for a diverse audience. Now let's look at optimization, because at the minute we have millions and millions of users interacting with the Blob Store to stream videos, and this is a serious bottleneck we need to address. Now, in a standard video streaming setup, leveraging something like a content delivery network proves to be a very efficient approach. So here's how it works. Videos are strategically cached across a network of servers distributed globally within the CDN. This ensures that content is closer to end users and reduces the latency, enhancing the overall streaming performance. Now, when a user initiates video playback by clicking the play button, the CDN comes into action. So instead of fetching video directly from the source or the origin server, the client interacts with the CDN. So it has points of presence spread across various geographic locations, where these points of presence contain the edge servers that store the cache copies. Now, when a user requests a video, so say this user down here is requesting a video, it's going to go to the nearest available edge server, optimizing the delivery. So we have two strategies to choose from. We have a pull CDN and a push CDN. Now, recognizing that a significant portion of videos may not attract substantial traffic on the platform, you have so many accounts with minimal followers, we can implement a targeted approach within our content delivery network. So if we use an 80-20 split, the Pareto principle, where a minority of content typically drives the majority of traffic, we can anticipate that around 20% of the videos will generate 80% of the overall platform traffic. Therefore, instead of proactively pushing all the videos to every edge server in a blanket manner, we can adopt the pull strategy. With this, we could set a threshold limit where videos that surpass the threshold based on views, for example, will be considered popular, and they can be cached across the CDN edge servers. And then we can dynamically adjust this so as videos gain or lose popularity, the system can intelligently update the cache, ensuring that the most relevant and sought after content is readily available at the edge servers. And only when there is a cache miss will it go to the origin servers, improving scalability, reducing latency, and providing that seamless streaming experience for users worldwide, which is something that was part of the requirements within our design. Along with this optimization, we'd look at increasing the number of servers at each point in the system to increase redundancy and be able to handle the heavy load the system requires. So this involves introducing multiple load balancers throughout the system to effectively distribute the traffic. And this gives us our final design. So as creators, we can upload to the system, which is going to go through this load balancer, which is going to distribute the incoming client requests to multiple web servers, and which is going to control things like permissions. It's then going to feed into the application server, which we know is going to be housing all the business logic. It's going to be doing all the heavy lifting. So when the user makes a post request, it's going to go through the system. It's going to update the metadata database with that information. The application server is going to send back some kind of token, which is going to allow the client to start uploading in chunks to the pre-transcoded blob store. Once this is carried out, a message is also going to propagate to the transcoding queue, upon which point these transcoding servers are going to see that event within the queue, and then they're going to start processing the video that has just been uploaded to the pre-transcoded blob store. It's going to transcode that video into multiple bit rates, multiple versions, and compress it, and then it's going to do a number of things. It's going to generate two events, one which is going to be published to the transcoded meta queue, which is consumed by workers to update the metadata database based on the video that was initially uploaded by the user. It's also going to publish a message to generate thumbnail queue, which is going to be consumed by these thumbnail gen handlers. And as we mentioned in the design, this is going to update the wide column DB big table with the thumbnails, because this is optimized for high read and write throughput. Lastly, this transcoding service is going to update the inverted index, which we are building using Elasticsearch. In terms of search for the user will have to navigate through the load balancer to the web server, to the application server, and then it will go into the inverted index if the user was searching by keyword. Now, if the user was searching by view count, again, it's going to propagate through the system. It's going to have to look in the metadata database for this information on the view count. Now, we have decoupled the system, so the actual view count is not updating with every single view the user makes. The view counts of videos are going to be stored in this KV store here, which based on this cron job is going to trigger these popularity servers, which are going to pull from the KV store. They're going to publish information into this queue, which is going to be consumed by the workers in order to update this database in batches. Now, in regards to streaming, we're effectively utilizing a hybrid approach of the most widely used protocols, MPEG- and HLS, to efficiently chunk and dynamically stream data based on the user network connection, further optimizing this process by adding global points of presence with the use of this CDN. Only if there is a cache miss will the CDN reach out to the origin server to retrieve that information from the blob store, significantly improving latency and offloading requests to the origin server. And finally, we have a deduplication service that runs based on the cron job, removing duplicates and optimizing for storage. So that's the design, a fairly complex one, but I feel like we've met the specifications set out in the requirements. Definitely an interesting one. Now, in terms of further discussion, so we have capacity estimations on thumbnails. So these were left out in this design, so you can go ahead and add them in. There's also social interaction. So explore the integration of social interaction features, such as comments, likes, and sharing. And then lastly, there's integration of shorts. So you'll need to consider any specific requirements or optimizations for handling shorter content. This could be a design in itself, but again, it's going to be one of those ones which is really interesting. With that being said, that's it for this video. Hope you found it useful, and I'll see you in the next one.